Welcome to ReLU Radio, the podcast where we unpack the latest and greatest in machine learning research. I'm your host, Adam, and today we're diving into a fascinating paper titled The Llama 3 Herd of Models from researchers at Meta AI. Joining me to break it all down is my co-host, Eliza. Welcome, Eliza.
Thanks, Adam. I'm excited to discuss this paper. It's a real doozy, covering Meta's latest and greatest language models.
Absolutely. Let's start with the core concept. What's the big idea behind Llama 3?
Well, Llama 3 is Meta's newest family of large language models designed to push the boundaries of what's possible in natural language processing. The key innovations here are in scale, data quality, and a focus on multimodal capabilities. We're talking about models ranging from 8 billion all the way up to 405 billion parameters.
Wow, that's a massive scale-up from previous versions. Can you give us a quick overview of what makes Llama 3 special?
Sure thing. Llama 3 is built on three key pillars: high-quality data, massive scale, and a focus on simplicity in design. They've put a ton of effort into curating a diverse, high-quality dataset, scaling up their training infrastructure to unprecedented levels, and keeping the model architecture relatively straightforward. The result is a family of models that can handle everything from basic language tasks to complex reasoning, coding, and even multimodal inputs like images and speech.
That's fascinating. Let's dive into the introduction. What motivated the development of Llama 3?
The main motivation was to create foundation models that could serve as a basis for a wide variety of AI tasks. The team at Meta recognized that modern AI systems are increasingly built on these large, general-purpose models. So they set out to create a new set of models that could handle everything from multilingual text processing to coding, reasoning, and even tool use.
Interesting. And how does Llama 3 compare to its predecessors?
It's a significant step up. The flagship Llama 3 model has 405 billion parameters and can process up to 128,000 tokens in its context window. That's a massive increase from Llama 2. But it's not just about size. They've also made big improvements in the quality and quantity of training data, using about 15 trillion multilingual tokens compared to Llama 2's 1.8 trillion.
Let's zoom out a bit and look at the general overview of how Llama 3 was developed. What were the main stages?
The development process can be broken down into two main stages: pre-training and post-training. In the pre-training stage, they convert a massive amount of text into tokens and train the model on next token prediction. This is where the model learns the structure of language and absorbs a ton of world knowledge.
And what about the post-training stage?
Post-training is where they fine-tune the model to follow instructions and behave more like an assistant. This involves supervised fine-tuning on instruction data and a technique called direct preference optimization to align the model with human preferences. They also integrate new capabilities like tool use and improve things like coding and reasoning abilities.
Let's dig into the pre-training process. What kind of data did they use?
The pre-training data is really the secret sauce here. They put a ton of effort into curating a high-quality dataset from web crawls, books, and other sources. They used a multi-step process, including PII and safety filtering, text extraction, deduplication, and even custom parsers for things like math and code content.
That sounds like a lot of work. How did they determine the right mix of data?
They used a combination of knowledge classification and scaling law experiments. Basically, they developed a classifier to categorize the types of information in their web data and then ran experiments with small models to predict how different data mixes would perform at larger scales. The final mix was about 50% general knowledge, 25% math and reasoning, 17% code, and 8% multilingual content.
Interesting. And I noticed they mentioned something called annealing data. What's that about?
Good catch! Annealing data is a small amount of very high-quality data they use towards the end of training. They found that fine-tuning on this data could boost performance on key benchmarks without overfitting. It's like giving the model a final polish.
Let's talk about the model architecture. What kind of neural network are we dealing with here?
Llama 3 uses a pretty standard dense transformer architecture, similar to its predecessors. But they've made a few tweaks, like using grouped query attention with 8 key value heads to improve inference speed, and a special attention mask that prevents self-attention between different documents in the same sequence. They've also expanded their vocabulary to 128,000 tokens to better support non-English languages.
And how did they determine the optimal size for their models?
That's where scaling laws come in. They ran a bunch of experiments with smaller models to predict performance at larger scales. Based on these experiments, they determined that a model with 405 billion parameters trained on about 16.5 trillion tokens would be optimal for their compute budget of 3.8 times 10 to the 25 FLOPS.
Training a model this large must require some serious hardware. What kind of infrastructure did they use?
You're not kidding. They used up to 16,000 H100 GPUs, each with 80 gigabytes of memory. These were spread across Meta's production clusters, which use a custom AI server platform called Grand Teton. They also had to deal with some pretty intense storage and networking challenges.
I can imagine. How did they handle parallelism for such a large model?
They used what they call 4D parallelism, a combination of tensor parallelism, pipeline parallelism, context parallelism, and data parallelism. This allowed them to efficiently distribute the computation across all those GPUs. They had to get pretty creative with things like load balancing and dealing with numerical instabilities at this scale.
Sounds like they ran into some reliability issues. How did they handle that?
Yeah, running at this scale is no joke. They encountered all sorts of issues, from faulty GPUs to network problems. They developed a bunch of tools for quick diagnosis and problem resolution, including things like flight recorders for their communication library. They even had to deal with power consumption fluctuations of tens of megawatts across the data center.
Wow, that's intense. So once they had all this infrastructure set up, what was their training recipe like?
The training recipe had 3 main stages. First, they did initial pre-training using a cosine learning rate schedule. They started with shorter sequences and gradually increased the batch size and sequence length as training progressed. Then they did long context pre-training to extend the context window up to 128,000 tokens. Finally, they did an annealing stage where they fine-tuned on that high-quality data we mentioned earlier.
And how long did all of this take?
They don't give exact timings in the paper, but we're talking about months of training on thousands of GPUs. It's a massive undertaking.
Let's move on to post-training. How did they turn this language model into something more like an assistant?
Post-training is where the magic happens to make the model more helpful and aligned with human preferences. They used a multi-step process involving supervised fine-tuning, reward modeling, and something called direct preference optimization, or DPO.
Can you break that down for us?
Sure. They start with supervised fine-tuning on high-quality instruction data. Then they train a reward model on human preference data, basically examples of good and bad model outputs. Finally, they use DPO to further align the model with these preferences. They do this over multiple rounds, iteratively improving the model.
That sounds like it requires a lot of data. Where did they get it all?
They used a mix of sources. Some came from human annotations, where people would write out conversations or rate model outputs. They also used synthetic data generated by earlier versions of the model, and even data from other NLP tasks that they reformatted into a conversational style. They put a lot of effort into ensuring the quality of this data, using things like model-based quality filters, and even having the model itself help judge the quality of examples.
Llama 3 seems to have a wide range of capabilities. Can you highlight some of the key ones?
Absolutely. One of the big focuses was on coding. They trained a special code expert model and generated a ton of synthetic coding data, even using execution feedback to ensure the generated code actually worked. They also put a lot of effort into multilinguality, supporting 8 languages out of the box. For math and reasoning, they used techniques like chain of thought prompting and even had the model generate its own math problems. Long context understanding was another key area, with the model able to handle up to 128,000 tokens. They also trained the model to use external tools like search engines and code interpreters, which really expands what it can do. And they put a lot of work into factuality and steerability, basically making sure the model gives accurate information and can be easily directed to behave in specific ways.
That's an impressive range of capabilities. How did they evaluate all of this?
They used a wide range of benchmarks and evaluation techniques. For the pre-trained model, they looked at things like performance on standard language understanding tasks, robustness to different prompting styles, and even how well it handled adversarial inputs designed to trip it up. For the post-trained model, they evaluated on everything from general knowledge and instruction following to specific skills like coding, multilingual performance, and math reasoning. They also did extensive human evaluations to assess things that are hard to capture with automated metrics.
And how did Llama 3 stack up against other models out there?
Pretty impressively, the 405 billion parameter version of Llama 3 is competitive with or outperforms models like GPT-4 on many benchmarks. The smaller versions, like the 70 billion parameter model, are often best in class for their size. They also showed strong performance on things like long context understanding and tool use.
What about safety? That's always a big concern with large language models.
Absolutely, and they put a lot of effort into this area. They did extensive testing on safety benchmarks, looking at things like the model's tendency to generate harmful content or be susceptible to jailbreaking attempts. They also developed a separate model called Llama Guard that can be used as an additional safety filter. One interesting thing they did was to evaluate the uplift in capabilities for things like cybersecurity attacks or chemical/biological weapons knowledge. Basically, they wanted to see if having access to the model would significantly increase someone's ability to do harm in these areas. Fortunately, they found that the uplift was minimal.
That's reassuring. Now, once you've trained a model this large, actually using it can be a challenge. How did they approach inference?
Great question. They focused on two main techniques, pipeline parallelism and FP8 quantization. Pipeline parallelism allows them to split the model across multiple GPUs during inference, while FP8 quantization reduces the precision of the model weights to speed things up and reduce memory usage. They found that using FP8 quantization could improve throughput by up to 50% during the initial processing of a prompt, and it gave them a much better trade-off between throughput and latency during the actual generation of text.
Llama 3 isn't just about text, right? They also did some experiments with vision capabilities.
That's right. They developed a compositional approach to add image and video understanding to Llama 3. Basically, they took a pre-trained image encoder and added cross-attention layers to connect it to the language model. They also added a video adapter to handle temporal information in videos.
How did they train these vision capabilities?
They used a multi-stage process. First, they pre-trained the image encoder on a large dataset of image-text pairs. Then they trained the adapter to connect this to the language model. For video, they added another stage of training on video-text pairs. They put a lot of effort into curating high-quality datasets for this, including things like visual grounding data and synthetically generated structured images.
And how well did it perform?
Pretty impressively. On image understanding tasks, the 405 billion parameter version of Llama 3 outperformed GPT-4v on several benchmarks and was competitive with models like Gemini 1.5 Pro. For video understanding, even their smaller models showed strong performance, sometimes outperforming larger specialized video models.
They didn't stop at vision, did they? I heard they also did some work with speech?
You heard right. They developed a speech interface for Llama 3 that can handle both speech understanding and speech generation. For speech understanding, they added a speech encoder and adapter to the language model. For speech generation, they implemented a streaming text-to-speech system.
How did they train these speech capabilities?
They used a two-stage process for speech understanding. First, they pre-trained the speech encoder on a large amount of unlabeled speech data. Then they fine-tuned the whole system on labeled data for tasks like speech recognition and translation. For speech generation, they focused on improving the text normalization and prosody modeling components of their text-to-speech system.
And how well did it work?
The results were quite impressive. On speech recognition tasks, their system outperformed specialized models like Whisper on several benchmarks. For speech translation, they were competitive with state-of-the-art systems. They also showed some interesting capabilities, like being able to handle code-switched speech and engage in multi-turn spoken dialogues.
Wow, that's a lot to take in. As we wrap up, what do you think are the key takeaways from this paper?
I think the main takeaway is just how much progress is being made in the field of large language models. Llama3 shows that with enough compute, high-quality data, and careful engineering, we can create models that are not just good at language tasks, but can also understand images, videos, and speech. The focus on open release is also really important. By making these models available to the research community, Meta is enabling a lot more work on making these systems better and safer.
Absolutely. It's exciting to think about what might be possible with future iterations of these models. Any final thoughts?
I think it's worth noting that while these results are impressive, the authors are also upfront about the limitations and potential risks of these models. They put a lot of effort into safety and are encouraging responsible development. It'll be fascinating to see how the field continues to evolve from here.
Couldn't agree more, Eliza. Well, that's all the time we have for today's episode of ReLU Radio. Thanks for joining me to break down this fascinating paper on Llama3.
It's been a pleasure, Adam. Can't wait to see what groundbreaking research we'll be discussing next time.
Until then, keep learning and stay curious, everyone.